It's very reasonable. It's good. It's good. Okay, it's 9 o'clock. Courtney. Okay, let's get started. Good morning and good afternoon and good evening. So welcome again to this World River and Delta System Source to Sink webinar series. Today we invite Professor Courtney Harris to talk about the sediment dispersal. Use the numerical modeling as a tool, particularly focused on the Po, the Mississippi River, and the Ayeyarwady River system. And so before I introduce Courtney, so next week, because this is the Thanksgiving week, and also next Friday, we do not have a talk. Instead, we have a joint talks. It's coming Wednesday on November 25th. And Frances and Stephen, they will joint talk about the fluvial sediment supply to the water delta, how it's changed and why it matters. So please mark your calendar coming back next Wednesday. So we have a joint talk next Wednesday. And Courtney got her, the PhD in environmental science from University of Virginia, and it's a postdoc at USGS, and then coming to West Virginia Institute of Marine Science in 2001. This is the year I just finished my PhD. I think Courtney and I have a very short time overlap, but we keep contact, and also most recently we have a joint project in Myanmar, study the Ayeyarwady River sediment in the Andaman Sea. So Courtney's main research is numerical modeling on sediment, focused on the content on the shelf and estuary. I know recently she also tried to add the biogeochemical portion in her modeling work, and he focused on the California shelf, Gulf of Mexico, even locally, York River, Chesapeake Bay, New Zealand, Adriatic Sea, Italy, and in the Ayeyarwady and Thanlwin in the Myanmar. And many people published, very good people published, and also very clear, a very active role in the community modeling effort. So I think today she will give us a talk, give us kind of across the Po River, Mississippi River, and Ayeyarwady River. So Courtney, now is your turn. Please share your screen and put a presentation mode.
Right. Thank you for the introduction, and thank you to everyone who has called in or logged on for this talk. Can you hear me okay?
Yes.
Okay, great. So Paul asked me to talk today about some of the work that I've done offshore of a few large rivers. So the large rivers that I've worked offshore of are the Po River that empties into the Adriatic, the Northern Adriatic, the Northern Gulf of Mexico. So this is a snapshot of a numerical model run off of the Northern Gulf of Mexico. And then recently, Paul and Steve Keel and I have been working offshore the Ayeyarwady Delta. So I'm going to show you all some ongoing work from the Ayeyarwady, as well as some old published work offshore of the Po River, and then some kind of ongoing work that we've been doing in the Northern Gulf of Mexico. So I really focus this work on the numerical models that we have developed to try. One of my main research focuses has been to try to apply three-dimensional oceanographic transport models to the problem of being able to quantify where riverine sediment goes once it enters the coastal ocean. So before I get started with the technical parts of my talk, in the US, as Paul mentioned, we are getting ready to celebrate Thanksgiving. A week from yesterday will be our Thanksgiving Day, where most of us Americans will join with family and hopefully small groups of family to have a feast day. So in that spirit, I wanted to really give a big thank you to Paul for hosting this seminar series. It's really, the times have been pretty challenging for a lot of people over the past, since COVID hit. And it's been a really kind of a bright spot in my week to be able to watch the seminars live when they are broadcast at 9 a.m. my time, or with a glass of wine or tea in the evening by watching the YouTube link. So I appreciate Paul for doing this. It's been really a lot of interesting, thought-provoking talks.
You should also mention that I'm also a WBMSed alumni.
Yes, Vince is, and Paul is also one of our alumni from our department. So I also want to thank current and former WBMSed students. I'll be showing you some of the work from Matt Fair, who has been working in the Ayeyarwady model, and Danielle Tarpley has worked with some of the aggregation models that we've been working on. And I'll show some results from Julia Moriarty's biogeochemical sediment coupling. I also wanted to give thanks to colleagues from WBMSed, Steve Keel, Lin, and Carl and Margie Friedrichs. And I'll be showing work that I have been publishing with them. Lin is currently doing a postdoc with me, and she has been doing a lot of work to couple the sediment and the biogeochemical work. Okay, and also thanks to colleagues who have worked on the projects that I will be discussing, and there are really too many to list, but I will be showing some work from Chris Sherwood, Jaya Savitsky, Chris Jenkins, Dmitry Dukovsky. So thank you all. It's been really great to be able to work with all of these people, both colleagues and students. So here's an outline for the talk. I'm going to give you guys first some background in the modeling framework that my work has been based on. And so that is the COAWST and the CSTMS model. And then I'm going to go through 3 examples from my work. I'm going to start with the Po River and the Northern Adriatic, where we pretty much ran the straight CSTMS model. Then I'm going to show some ongoing work from the Ayeyarwady River and the Northern Andaman Sea. So that is work that I've been collaborating with Paul Liu and Steve Keel to try to predict the dispersal of sediment offshore of the Ayeyarwady. And then I'm going to close with work from a few different projects where we have been looking at sediment dispersal in the northern Gulf of Mexico, and specifically trying to quantify the way that the sediment impacts biogeochemical processes, as well as think about what are the processes that deliver sediment from the shelf and the rivers to the deep sea. And then I'm going to close with some summary and ideas for future directions. So the main points that I want to get across in my lecture is first that by working within a community model, that really helps us to make advances in terms of interdisciplinary science, as well as being able to kind of build on the work of our colleagues by working together within a common modeling framework. This has allowed us to develop 3-dimensional numerical models that, with my research interests, can account for suspended sediment transport. But because I'm working within a large community of modelers, we also have access to other modules in the code that can, for example, calculate the biogeochemistry of the system, as well as modeling components that can account for coupling between waves and the ocean water, as well as atmospheric processes in the ocean water. Another point I want to show is that if we look at a dispersal system, and I'll show the dispersal downstream of the Po River as an example of this, then if we look at a complete dispersal system, then there might be multiple sediment sources and also multiple processes that are acting to transport sediment from the source to the sink. And then the last 2 points is I'm going to show some of the work we've been doing to account for seabed geochemistry and in our model. And I want to close with the point of I think that the community, the source to sink community, would really benefit by having better ability to account for gravity-driven flows within our 3-dimensional models. So an overall theme for this series of lectures has been thinking about source to sink, sediment flux and fate. But we're not just limiting ourselves to being interested in where sediment is transported from the terrestrial sources to the continental shelf, estuarine, or deep water sinks. We're, in addition to being interested in that particulate transport, we also need to be concerned about the transport and transformations of the geochemistry along the transport pathways. So most of my work has been to look at the transport of suspended sediment on continental shelves. So specifically looking at sediment that comes in from the river, and then it is transported on the shelves, and then think about whether it will be deposited on the shelf or exported offshore. So I'm going to focus on these three river systems that I talked about. One reason we think about the river systems is that there's just such a huge input of sediment to the global ocean from rivers. So these figures here have been shown in several of the other talks during the seminar series, but I wanted to show them again as motivation for why we're looking at these riverine sediments. So the rivers input 19 gigatons per year of sediment to the oceans. And in addition, or along with these sediments, it's also a major source of carbon to the ocean. So the estimate from Bauer et al. Is that it's about 0.5 gigatons per year of carbon also transported to the oceans. So in order to understand the fate of this sediment, as well as the fate of the carbon that is coming in with the rivers, we need to understand what is happening in the estuaries and continental shelf as that material goes from the terrestrial riverine sources to the offshore sinks. These two cartoons are ones that I've used quite often to kind of illustrate the transport processes that occur when riverine material enters the coastal ocean. So this panel on the upper left is a figure from Don Wright, and he's showing in here an estuary emptying a freshwater plume out into a continental shelf. That plume is going to be deflected by Coriolis, as well as the along shelf flows. And then once the material, that sediment, gets out into the open ocean, it tends to settle into the bottom boundary layer. But there it can be resuspended by energetic waves or currents and transported either along shelf or across shelf. Now, when Don put together this figure, he was really thinking about suspended sediment transport. This figure on the right is a figure that I got from Peter Tchaikovsky and Rocky Geyer. And to this idea of resuspended transport, they added a few processes. One thing they added was the idea that when our fresh water comes into the coastal ocean, the salinity in that going from fresh to slightly salt water is going to enhance flocculation. So the sediment particles, those fine-grained sediments that are leaving the river plume, are going to form larger aggregates where they will settle into the bottom boundary layer. So they would be transported by ambient shelf currents as suspended load. They might be resuspended by energetic waves. But one thing that we found in past studies is that this material can form near bed gravity-driven flows. So they added to this cartoon the idea that we can produce downslope cross-shelf turbidity currents, is what they labeled it. The nomenclature now for a continental shelf might be to call them near bed fluid muds, or wave-supported gravity flows, or current and wave-supported gravity flows. But the main idea is that when you suspend sediment near the bed, that addition of that suspended sediment can stratify the flow and trap the sediment in a thin layer that then the added pressure force will cause that material to flow down slope. So a major goal of my research has been to try to account for these processes, the suspended load, as well as the gravity load, and the flocculation within a three-dimensional numerical model so that we can predict the transport of sediment from the riverine source to the off-shelf sink. Now, the way that we've gone about trying to make these advances is not to work alone in a vacuum on code that we write ourselves, but to work within a large community. So over the past 5 years or so, I've been relying on the COAWST modeling system. So this stands for Coupled Ocean-Atmosphere-Wave-Sediment Transport, COAWST modeling system. And this was really a modeling system that was built mainly, the main developer being John Warner from the USGS. And this photograph here was taken at Paul Liu's home institution in February 2019 at the COAWST user group meeting. So I include that just to show that there's a large community of modelers and oceanographers and atmospheric scientists working on developing these coupled modeling systems. So here, this is a schematic of what is included in the COAWST system. So it has the ability to couple an atmospheric model, the WRF model, to the ROMS ocean model. So ROMS would calculate the transport of the ocean water. The WRF would be calculating the winds, and then the coupling between them would account for heat fluxes and freshwater, like precipitation fluxes between the atmosphere and the ocean. The modeling system also includes the SWAN wave model. So based on the winds and the ocean currents, you can calculate the wave energy. And it's really, in order to predict suspended sediment transport, we need to know something about both the waves and the currents. So my group, so the COAWST system gives you all of these things: WRF, SWAN, ROMS, as well as the sediment transport model. They're linked with the model coupling toolkit. Now I'm going to show applications where we've used the COAWST system, but within my group, we have mainly used the coupling between the ocean and the sediment model. So all of the examples I'll show use that. But sometimes some of my applications have also coupled the SWAN wave model with the ocean model to predict the sediment transport. And then another thing to add is that since we're using ROMS as our ocean model, it includes modules for the hydrodynamics of the ocean to predict the transport of salinity, temperature, and momentum in the ocean. It includes the sediment transport model that I use, that I'll describe in another slide or two. But it also includes modules for other things, such as the biogeochemical model. So by working within this community model, we are able to focus on our own area of expertise, which is the sediment transport, but take advantage of advances in the modeling coupling with hydrodynamics, waves, and even biogeochemistry. So within that COAWST system, then there's what I call the Community Sediment Transport Modeling System, so the CSTMS. This model, the sediment transport model, is described in Warner et al. 2008, and it's implemented within the ROMS model. But I think it's worth noting that versions of Warner et al.'s 2008 model have also been put into other hydrodynamic models. Specifically, I know of versions of it being in 2 finite volume models, FVCOM and SCHISM. The version, though, that I've worked on has always been the one implemented in ROMS. Now, as described in Warner et al. 2008, the model assumes that sediment has non-cohesive behavior. That means that the model does not account for aggregation and disaggregation. You put in a certain amount of each sediment class, and then that material is moved around, but the different sediment classes don't react with each other. So it's kind of mass conservative for sediment unless it's moving in or out of the boundary. In the past couple of years, Chris Sherwood has published kind of an extension to the community sediment transport model that does account for cohesive sediment. So this version from Sherwood et al. 2018, it does account for flocculation and also bed consolidation. But most of the applications of Warner et al. That are in the literature, like this paper has hundreds of citations, most of these applications are assuming non-cohesive sediment transport. So this schematic here shows kind of the basics of how the sediment bed model is put together. So the Warner et al. Model lets ROMs run the hydrodynamics and calculate the suspension, the suspended sediment transport. And then underneath the hydrodynamic model, it has a sediment bed model that keeps track of the amounts of sediment that have been deposited to the bed and the grain size fractions on that bed. So when you run the Warner et al. Model, you're adding a sediment bed grid kind of underneath your hydrodynamic grid. So that's the background in the modeling that we have been working on. Now I'm going to show some examples of the use of that sediment transport model from some of my past and current work. So the first example, Paul specifically asked that I talk about the Po River, and I was happy to do that. But this is work that was done a while ago. So my paper on this came out in around 2008. And what you see on these slides is this panel here. This is a figure from Pellegrini et al. The green represents the thickness of the Holocene sediment deposits. So you see that there is a Holocene sediment deposit around the Po River Delta. And then as you travel down along the coast, the deposit thickens here along the Gargano Peninsula. And so one of the research questions was, well, we have our largest river source several hundreds of kilometers north of where we have some of our thickest deposits. So can we explain what are the transport processes getting things from this source to that sink? This satellite image shows that along the west coast of the Adriatic, you have frequently you have these turbid waters traveling down the coast. And this is suspended sediment that's being carried by the Western Adriatic coastal current. So what my group, so I've heard some people call this the Po River dispersal system, but today I want to kind of try to convince you that maybe we should call it the Apennine margin dispersal system, because a lot of the sediment is coming in from other rivers other than the Po. So this is a plot of the model grid that we developed, and each of the little blue triangles around here represents a source of fresh water that we put into the model. So we have several distributaries up here at the Po River. These little triangles over toward the Croatian coast represent groundwater and river sources that did not carry much sediment. And then all these triangles here, these represent what we call the Apennine rivers. So we included sediment from 15 different rivers. We ran our model to represent September to July of, I think it was 2002. And here we see that we had high Po River discharge during December of that year. And this top panel is the wave height. So we see that the waves tended to be more energetic during the winter months. So a little more on the sediment input that we used. The Po River is the largest river emptying into the Adriatic. As I said, it delivers about 15 million tons of sediment per year. However, between the Po River and this sediment sink at the Gargano Peninsula, there are 14 other rivers that collectively we call the Apennine rivers. So from the Reno River in the north down to the Ofanto River in the south, these rivers, I think this is the pre-anthropogenic load, carried 32 million tons of sediment per year. So these rivers input twice as much sediment collectively as the Po, even though any one of those rivers is not really a very large river. But because they drain very steep mountainous terrain, they carry heavy sediment loads. So I'm going to show you an animation of the model run. give you a sense for the time and space scales that we were running. This left-hand panel will be the wind and waves. The second panel is the hydrodynamics in terms of salinity as the color and the ocean currents as the arrow. These next two panels show the suspended sediment transport of material that was entered by the Po River and the Apennine Rivers. And then the final panel will show erosion and deposition on the bed, with erosion being blue and deposition being red. So let me get them. I have to get the model to, I have to exit. Okay. All right, so now what you're seeing is the Adriatic has two main storm wind directions. One will be winds from the northeast, and those are the winds that really set up our coastal current. The others are winds from the south. Those are the Sirocco winds that tend to kind of retard the coastal current, and they also are responsible for their flooding events in Venice. I'm going to go up here to the time of when the flood starts. So now in December, remember, we had large sediment inputs from the Po River. So we're getting a lot of salinity. This blue is the freshwater plume making its way down the coast. But when we look at where the sediment is going, a lot of sediment from the Po was trapped up in the northern Adriatic. These Apennine rivers, however, are really being entrained into that Western Adriatic coastal current and transporting down southward towards our depot center. So when we look at how the model behaved over the entire time, so here in this top panel, I took the model calculations and I averaged or integrated them for the entire 9-month model run that we did. So these are the average wind speeds and our wind stresses and directions. This is the average wave orbital velocity. So our waves are most able to suspend sediment in the shallow water. This is the time average current and sediment concentrations. So we see the Western Adriatic current carrying sediment southward. And then this is the sediment flux. So it's the product of the currents times the suspended sediment. So we see that our sediment flux from the Po, a fair amount of that material gets caught in this northern Adriatic gyre. And we have high sediment fluxes going down the Apennine coast. When we look at, for some verification of the surface fields, I compared the salinity, or not the salinity, the satellite image from January 2003 to our surface modeled calculations. And so in both the satellite and in the model run, we see that we have this northern Adriatic gyre entraining some of that Po sediment and transport down southward by the Western Adriatic coastal current. So to close this part of my talk, I'm showing the overall modeled distribution of the Po and the Apennine sediment. So we do see that some of the Po sediment during this 9-month model run does make it down here to our Gargano Peninsula deposit, but a lot of it over the timescale that I modeled is trapped in the northern Adriatic. In contrast, this Apennine sediment, most of that is captured by the Western Adriatic coastal current and travels southward. And then finally, to try to explain the presence of this Gargano deposition, I compared my calculations of bed shear stress to lead-210 based accumulation rates that Cindy Palinkas obtained. So Cindy got these mass accumulation rates based on lead-210. She sees an increase in accumulation as you go toward the Gargano Peninsula. And in the model runs, you see a decrease in bed shear stress as you go that way. So I would say then that this, to explain the processes that are causing this deposition, we can think of it in terms of we have sediment transport through the Western Adriatic coastal current, and we have flux convergence here because this area has lower bed shear stress. It has lower bed shear stress both because the waves tend to be lower here because the Gargano Peninsula acts to shelter some of the wave energy, and it's out when the waves are from the south, they're sheltered by Gargano Peninsula. When the waves are from the northeast, they tend to be most energetic in the northern Adriatic. So this area has lower wave energy, and it also has lower current speeds. So that causes sediment to drop out and be deposited here. But so to summarize, we used our 3D ocean model. It was run with a wind model and a wave model. We reproduced depositional patterns both near the Po Delta and down near the Gargano Peninsula, but these Apennine rivers contribute significantly to the deposition at those at the Gargano Peninsula. Okay, now the second example that I'm going to show you is some ongoing work that I'm doing with Steve Keel and Paul Liu, and a student here at VIMS, Matt Fair, has been doing the actual model runs. And so we've been looking at sediment dispersal offshore of the Ayeyarwady and Thanlwin rivers. And our motivation for doing that is maybe threefold. One, this is a major global source of sediment to the coastal ocean, okay? So, and it's not been studied to the extent that Paul and Steve have been able to study in the past couple of years. So before they were able to do their field work, where they obtained sediment cores and chirp profiles along these track lines and coring locations, there was really not much known about the seabed in this site. Okay, but it's a major input of both carbon, maybe second in the world, I think, in carbon inputs, and of sediment. And then another reason that it's been so interesting to study is that the processes that are happening here, I think, are going to be or would be a really good point to have in terms of our understanding of both sediment and carbon recycling in continental shelves. And the reason is that the processes here are not seem very different than the processes that at least I am familiar with that we've studied for source to sink offshore of other large river systems. This is a very tidally dominated system. These are M2 tide amplitude plots from a paper from 2013, and it may be hard to see, but these are the amplitudes of the tides and as these solid lines. And what it shows is that as we move from the open Bay of Bengal over towards the western coast of the Gulf of Martaban, that our tide amplitudes get very large. We have higher than 5 to 7 meter tides along this coast. It's also an interesting system in that it's a monsoonal system. So here, these panels here, the arrows represent the average wind direction. The blue line represents the average river discharge, and then the green line represents the wave energy. So we see that during the summer times, when we have the southwest monsoon, we have very energetic waves, we have winds blowing shoreward, and we have our highest discharge amounts. Conversely, during the northeast monsoon time, during late fall to early spring, winds tend to be slightly weaker and blow from the northeast, discharge is low, and wave energy is lower. So going into this, we thought, well, there might be very different dispersal patterns between the southwest monsoon and the northeast monsoon. And that's an idea that has been around in terms of the ocean circulation for some time. So Paul had this figure in his paper showing what is believed to be the case for ocean circulation during the times of the southwest monsoon, shown in red arrows, and the northeast monsoon, shown in blue arrows. So during the times of the offshore winds during the winter, it is thought, based on historic data of ship tracks, that the currents would flow out and we would be exporting material out of the Gulf of Martaban and into the open Bay of Bengal. Conversely, when the winds blow from the southwest, It is the historic data for surface currents showed that on average, the currents would be coming into the Gulf of Martaban. So we would be acting to kind of trap the sediment from the Ayeyarwady River and the Thanlwin River within the Gulf of Martaban, where maybe it would collect and then perhaps escape down into the deeper Andaman Sea. But again, these ideas of circulation are based on kind of historic data, like historic in that it's even older than I am, and I'm getting up there now, but it was data from the publication came out in 1960. So, you know, that data is pretty old. It's based on only what's happening at the surface, and a lot of the sediment transport would be happening subsurface. So that's left us with the questions of what's going on in terms of sediment transport, and can we improve upon this knowledge of the circulation? And another thing I want to add is some other papers have looked, used now 3D hydrodynamic models and shown that while these conditions do hold on average, that on average the southwest monsoons cause flux into the Gulf of Martaban. On average, the northeast monsoons cause export from the Gulf of Martaban to the Bay of Bengal. That in reality, the situation is that the currents are fluctuating. So while you may have on average the surface waters going out, you're going to have significant amounts of time when those currents reverse, either due to tides or due to wind forcing or other larger scale shelf waves that cause fluctuations in the current. So in December 2017, Paul and Steve Keel went and did I think they were out for about 2 weeks and took chirp and sediment core data from this study site. So they had a really successful cruise, and they've both been able to publish some of their results. Paul's paper came out in 2020, Steve's paper came out in 2019. So I wanted to highlight some of their results. Here, Paul plots the Holocene thickness, and I believe he got this from his chirp surveys, showing that the thickest sediment deposits are kind of in this area offshore of the Gulf of Martaban. Okay, Steve, based on looking at the layering and the sediment cores that he took, saw that this area inshore of the Holocene deposit was very well mixed. There was a lot of evidence of intense seabed mixing, not so much evidence of bioturbation. So it really made it look like the sediment was being constantly stirred, but the accumulation rates were not very high. And so that gave him the idea to conceptualize this as an intense seabed mixing fluid mud reactor. That means that we're mobilizing the sediment, putting it up into oxygenated water on the tidal cycle, and kind of keeping that material actively resuspended before some events would happen and cause it to escape the Gulf of Martaban mixing layer and go offshore. So what we wanted to do was, or what we're working on now, is developing a three-dimensional model that can kind of test these ideas. So Matt Fair, who is a graduate student here at WBMSed, has been developing a wave hydrodynamic sediment transport model. Like our other work, it's based on the COAWST modeling system. And he's using it to look at research questions such as, what are the important temporal cycles in dispersal? We came into this thinking that we would see a big difference in the seasonal behavior of the system, but so far his model results actually show that the tidal variation is more significant than the seasonal. We are looking to see whether we see big east to west differences in dispersal, and we're trying to see what would be the residence time of sediment in the Gulf of Martaban, and what processes can allow that material to escape the Gulf of Martaban, and when it does escape, would it go downhill into the deeper Andaman Sea, or will it go westward into the Bay of Bengal? So this is a kind of schematic of what Matt has included in his model. And I'm going to show you some of the results now from his model. One thing that we see, so in these plots, he plots as an arrow the average current, and then he plots as an ellipse the variation around those average currents. Now I want to point out that for purpose of scale, the currents, the arrows are plotted at a much smaller scale than the variation. So the take-home message here is that the tidal velocity variations are really large compared to the residual or average current. The top panels show the calculations for August, and the bottom panels show the calculations for January. The left-hand panels are the surface. So in the surface, we see that Matt's calculations follow that expected pattern that under the southwest monsoon, we get import of surface water into the northern Andaman Sea. During the January conditions, we get export. But when we look at what's happening on the bottom, we get import during the southwest monsoon, but we also get import during the northeast. We don't get, on average, export of these bottom waters to the northeast. Now, we are going to get times when material is exported because those tidal variations are so large compared to the residual. We see intense resuspension in the Gulf of Martaban. So for this figure, Matt took his bed shear stress calculations, and he looked at the frequency or the percentage of time at which it exceeded a threshold for resuspension. And so we see that in the Gulf of Martaban, 90% of the time, the flows are energetic enough to resuspend sediment. So this is the figure for August, but the figure for January looked very similar because the system is tidally dominated. So the differences that we see between the different wind forcing didn't really impact the resuspension. And then here, this is showing the tidal, this is another animation. This is showing the fluxes of sediment. So the arrows again are current velocities that I believe is the depth average current, and the concentrations are shown as the depth average concentration. So we aren't, this is a preliminary result. Steve Keel showed a similar movie during his talk, and so I wanted to revisit this a bit. We're not confident as we would like to be over the concentrations that we have in the water column, but things that I want to point out is that a lot of our sediment is focusing on the eastern side of the Gulf of Martaban. That's because the tidal energy is higher there. And also, we see this tendril of material kind of escaping to the deep sea. And Matt has run another model where he does not account for the extra density of the sediment in the water. And when he does that, he doesn't get this tendril of material escaping to the deep sea. So to the resolution that his model has, this system is setting up kind of a gravity current that is flowing, this denser flow flowing down into the deeper Andaman Sea. But it's subject to change, as I said, because we're still doing sensitivity tests, mostly with the sediment characteristics. So to summarize what we've seen for the Ayeyarwady Shelf in the Gulf of Martaban, the tidal processes are dominant. We get very high sediment concentrations and intense reworking within the Gulf of Martaban. The seasonal differences that we see are more due to having higher sediment and freshwater input during the summer monsoon than during the winter monsoon than we get compared to the wind and wave forcing. And what we're doing now is more sensitivity tests so that we can hopefully have more confidence with regard to the way we're modeling the sediment properties. But then what would we think would be important to do next for this region? As I said earlier, that the Ayeyarwady and Thanlwin rivers supply a globally significant amount of organic carbon to the coastal ocean. These are schematics from a paper from Jim Bauer showing the processes that organic carbon undergoes as it goes from a source to a depot center. And because this region has these intense fluid muds, which we saw in CTD data, as well as the evidence from Steve's cores, as well as our high concentrations in our model, we really don't have a good handle on how those processes behave in this tidally energetic, sediment-rich area. And so in order to be able to model it, I really feel that we need some field observations of the sediment transport processes so that we can have more confidence in our sediment concentrations and our turbulence concentrations. And we need to do that in order to evaluate how transport processes can be interacting with the biogeochemistry. Okay, so my third example and final example is thinking about processes in the northern Gulf of Mexico. And my work here, our group's work here, has been really focused on 3 issues. One is trying to evaluate how sediment resuspension might impact hypoxia or areas of low oxygen. Another is to think about how sediment processes impact oil spill dispersal. So this figure is from a paper from Valentine. The blue here is the tracking of surface plume of oil on the water surface. And then these contour lines are tracking where oiled sediment was deposited on the seafloor. So in order for these oiled sediments to deposit on the seafloor, the oil aggregated with marine snow and also sediment particles, which made the oil settle to the seafloor. But we don't have really the ability to model, we have not had the ability to really model those processes. So my group's been working on trying to bridge the gap between calculating suspended sediment dispersal and how it impacts its biogeochemistry. And then finally, we need to think about how sediment is delivered to the deep sea. In this region, it's really important because there is a lot of oil and gas infrastructure, and there is evidence of turbidity currents that have caused oil contamination events, pipeline breakage, that then is very difficult to deal with because of the intense water depths. So first, I want to show some results from our work where we coupled the sediment transport model with a biogeochemical model. So Kevin, day before yesterday, Kevin Shu gave a great talk where he presented his work modeling suspended sediment transport in the northern Gulf of Mexico. And what my former student, Julia Moriarty, did was she took Kevin's sediment transport model and linked it with a biogeochemical model that Katja Fennell had developed in order to account for the way that transport of organic matter and deposition of organic matter and then resuspension of that could impact oxygen consumption on the shelf. So she ran her model for a 2-year period, and here this is showing the forcing in the model. This shows the maximum bed shear stress and then the frequency of resuspension, with red being almost always resuspended and blue being never resuspended. And so one thing that Kevin noted in one of his papers was that this frequency, the area that's frequently resuspended is kind of inshore of the area where hypoxia occurs. So Julia wanted to kind of test this idea to see if this resuspension stirred up organic carbon that then was transported off shelf. And then when that material was resuspended, it would come into a bottom stratified layer that could consume oxygen. So here are some figures from her paper. And these figures here show her model calculations for particulate organic carbon, the remineralization rate of the material that's in the water column, and then the bottom water oxygen concentrations for June 2006. So in this model, she used resuspension. She ran another model where she turned off resuspension. So these panels show the difference between the two. So where it's blue, that means that resuspension added that tracer to the model. So resuspension added particulate organic carbon to the model because it's resuspending the material from the seabed. That increased the remineralization rate in the bottom waters because you've got more organic carbon in the bottom waters, and that decreases the oxygen. So by including resuspension, her oxygen consumption rates went up, I think, by about a factor of 2. Another way we've been trying to put our model together with using our coupling ability to couple models is we've been working with the CSOMIO group, which is, I think, the Consortium for Oil and Microbial Interactions in the Ocean. So this has been headed up by a group at Florida State. And we developed a coupled ocean, a COAWST model that included the ROMS hydrodynamic model, as well as the phenyl biogeochemical model, which was, this component was developed by Victoria Cole's group at Horn Point. Dmitry Dukovsky put in a 3D oil transport and weathering model. And then my group, Lin specifically, added an oil particle aggregate formation model. So Lin took a flocculation model that's available in ROMS and modified it so that instead of aggregating sediment particles together, it is aggregating oil droplets and sediment to form these OPA that then would settle to the seabed. We have a couple of papers that we just submitted just last week that describe our model formulation for the OPA, and Dmitry Dukovsky submitted a paper that shows how this full coupling model works. So this panel is his calculations of where oil is in the water column. And then over here, this is where the model formed these oil particle aggregates. So it's tending to form them in places where we have sediment suspended, as well as we have a lot of oil. And he placed his oil contamination at the site of the Deepwater Horizon oil spill. And then finally, the next thing we've been trying to think about is how we transport sediment to the deep sea. And so this was part of a group that was spearheaded by Systems, the Community Surface Dynamics Modeling System. And here we're trying to think about source to sink transport. We get sediment in from our rivers, and we want to think about what processes trigger the delivery of that sediment to the continental slope and beyond. Wanted to look at especially the role of large storms and what could potentially be triggering turbidity currents. This is our model workflow. This paper came out in last summer, and it shows all the model components that we have combined, okay? To get our Riverine inputs, Sagi Cohen from, I think it's at University of Alabama, ran the WBMSed model to give us riverine inputs from the Mississippi River, the Atchafalaya, and also a series of smaller rivers that do deliver fresh water and sediment. My group looked at suspended sediment flux, and I'll show one last animation. This shows where the suspended sediment goes over the course of the model run. The bottom panel, the red line is river discharge, the blue line is wave heights. So we're going to come up here, and this is plotting the model results in a transect through Mississippi Canyon. So as a river starts to reach its peak discharge, we'll see some freshwater lenses delivering sediment out, but those concentrations are not especially high. When we get up to our storms, we had 2 hurricanes during this time. And so as we approach the hurricanes, we'll see intense remobilization, resuspension on the shelf that sends sediment eventually out over the continental shelf and slope, and that material settles out. So it turns out that the time it takes for that nepheloid layer to settle out to these deep water depths tends to be days to up to like 10 days. So that gives a lag time in delivery of suspended material to the offshore just from the settling of the material through the water column. And then my colleague Chris Jenkins developed quantitative methods to try to account for turbidity current ignitions. So during the hurricanes, he would predict at these stars, he would predict the wave loading and the steepness of the slope to potentially cause turbidity current ignitions at the points marked by the stars. So then to summarize, for the Northern Gulf of Mexico, we've been working again within a community modeling system that facilitates our interdisciplinary studies. Resuspension and transport were shown to increase oxygen consumption. And we're working on linking our sediment model to better account for oil particle aggregation or even marine oil snow during oil spills. And our thinking about suspended sediment delivery to the deep, in our model calculations, the suspension delivery to the deep was definitely dominated by the hurricanes, not by smaller storms, and not by flood dispersal. And those storms also seem capable of igniting turbidity currents. So I will stop here. I'll stop here and just leave my closing thoughts up on the screen. Thank you.
Thank you very much, Courtney. It's a great talk. Particularly, we can see, your 15 or 20 years ago, the work in the Adriatic Sea, now in Andaman Sea and the Gulf of Mexico. I think the model become more complex and more interesting. So can do a lot of more work. So let's see if you have any question. Let me just turn on the function. You can unmute yourself and go ahead to ask. So I saw Michael Steckler unmute himself. Do you have any question? Gil?
It was more of a comment on the Po system is also really interesting because during the, so Courtney shows what's happening during a high stand where the sediments are going along the coast, but then during the low stand, the northern shelf is all subaerial and all the Po and the other rivers gather into a tributary and dump into the mid-Adriatic deep, and the Gargano becomes completely starved of sediments during the low stand because that coastal current cuts off. So there's a very different geometry of sediment transport in the high stand and low stand.
And at one time I tried to model that, but it's been a while.
Yeah, no, it's been a while for,
Yeah.
well, yeah, I think my paper was also around 2007 or 8.
So anybody? I saw Chris J. Unmute.
Yeah, so Chris Jenkins here in Colorado. So
Okay.
thanks for the update, Courtney. It's always lovely to look at your work. I'm just really impressed at how much sort of detail there is in the Ayeyarwady area, for instance, the tides and so on. It's a very impressive data compilation. So turning to the Adriatic, we've recently updated the DB seabed coverages there, and there are some interesting things coming about with the new data, and it may affect a lot of deltas actually. So the organic carbon coming out from the delta is fostering a whole lot of growth of small reefs. So the Italians have investigated these recently, and there's a what would you say, a total scattering of small reefs growing from the organic carbon supply from the delta. And these are in the northern part with that eddy. So one of the interesting things is that the seabed roughness in that area is really changing. And so your models may need updating for the bathymetric roughness on scales of 10 meters or so and 2 or 3 meters height, even in fairly shallow water. Right, so this I think could really be a factor in the sediment trapping on the scales you're working at.
Yeah, that's really interesting. And
Yes.
I haven't worked on that model in quite a while. And when I was putting the talk together, I think the model runs might be older than my children.
Right.
And they're almost driving now, but not quite. But
I bet your children think the models are cool. So that's important as a parent.
No, but anyway, but there are lots of papers out that are still using this modeling or updates to this modeling system. The Italian research community has been doing a lot of really interesting work with water quality models as well as gravity current models of trying to deliver sediment to the deep Adriatic. So hopefully those research communities are cognizant of the advances in knowledge of the bed roughness.
Okay, very good, thanks.
Gail.
Really nice talk, Courtney. I really enjoyed it. I think it's really curious about the Ayeyarwady, and like many systems where gravity flows and fluid muds may be responsible for a lot of the transport and a lot of the biogeochemical processing, it's often like they're just sort of hints that they're there and that they're active. And I think you mentioned, that, more field data might be needed. Do you know if there are plans and what kind of, strategies would there be to try to get the kind of information that you seek?
Well, I know, we did propose last year to go and get some water column measurements and geochemical measurements. And so the plan that I think needs to be done would be to have some instrumentation in place to get measurements over spring neap cycles. In a way, it's the fact that it's a tidally dominated monsoonal system is kind of nice. It makes it more predictable. We don't need to wait for a massive hurricane to come by to get measurements that are going to be relevant over the annual to maybe even decadal time scale. So I think targeting a spring neap cycle, in the model runs at least, we see a lot of variation in suspended sediment over the spring neap. I think targeting the summer months when the discharge is highest would make the most sense. And I think getting measurements of potential stratification in the water column. When Steve and Paul were on the cruise, Danielle Tarpley went with them, and Danielle operated a CTD cast, and she saw what looks like fluid muds a couple of meters thick in the Gulf of Martaban. So it would be nice to be able to get more evidence of that and the timing of them. Off the boat, they also took ADCP, and I've been working with an undergrad student who's analyzing the ADCP data. And from the backscatter of the ADCP, there's one transect that they took on an ebb tide. They kind of started at slack water and went southward. And you can see in the ADCP backscatter, as the current velocities increase, a layer forms. And so it looks like it's a tidally modulated fluid mud layer forming along that transect. And, it's anecdotal evidence because it's one transect during one ebb tide, but it would be really cool to get time series data.
Yeah,
look at
it is really cool. And it is like a lot of systems where we found fluid muds or gravity flows to be important. It's like just these little hints that they're there, and then they turn out to be really important, for a lot of the different processes. So good luck if you end up doing more work.
Thank you.
And one thing I would like to see is the Ayeyarwady NMSC system. What we have done so far is only scratched a little bit of the surface. There's many unknown. We kind of open an unknown box. And so hopefully, I don't know, it's still possible or not. If we can have the kind of like onset, that kind of interdisciplinary, multidisciplinary, group collaborate effort over there, that would be wonderful, because such a big reverse tropical system with a combination with tectonic, large river, human impact, tidal dominated tropical, it's a wonderful system to work as a team. And I don't know, maybe we should have some small workshop to discuss this. Okay, Elizabeth?
Hi, yeah, nice talk, Courtney. As you know, my interest is always in the organic carbon, so my ears really perked up when you showed that figure that you coordinated with Katja. And so my question is that the only place you've done that coordination where you have some idea of what the organic carbon is doing? And yeah, just curious, because that was kind of, that for me, that was really interesting.
So Julia Moriarty's Gulf of Mexico work. Julia has 3 papers, and so this was part of her dissertation work. She's now faculty at University of Colorado, and Margie Friedrichs and I co-advised Julia, and she has 3 publications. One, she applied the model offshore of the Rhone River and used Christophe Rabouillet's group's data to kind of verify the seabed model. The other location was the Chesapeake Bay. So she has a paper that I think came out in 2020, where she used Margie's Chesapeake Bay model and added the resuspension and redistribution of organic matter to that. And I'm working now with postdoc Thanlwin. We're working on a Gulf of Mexico project where we're trying to use some of Kanchan Maiti's data, where he has sediment bed microprofiler data, but that works. I wasn't ready to show that today. So, but that's Gulf of Mexico again.
Yeah, really interesting. Thank you so much. It's just like, it's nice to see that organic carbon component is, you're getting at that. Yeah, and that's nice.
And the main, like a big part of it is where is the transport of the organic carbon. As I thought the diagenetic piece would be really huge, but it's actually where you put the carbon that seems, from Julia's work at least, seems more important. So.
Okay, I'll try and find those papers. Thank you.
Well, Paul asked me to put, here's references. It has Julia's Gulf of Mexico paper, but you know, yeah.
Thanks. I'm gonna take a screenshot of that.
Okay.
Good to see you. Great talk.
Good to see you too.
Okay. It's wonderful, and I think this talk, if you want to rewatch, or if you're a student, you want to give a student to watch this, and is on the YouTube. You can go to tinyurl.com/source2s2s talks. So all the talk will be archived there. And I would also like to mention the next Wednesday, we have a joint talk given by Francis and Stephen, talk about the sediment supply to the world delta. So please mark your calendar, do come back next Wednesday. And
okay, thank you.
So Courtney, I guess if possible, and I mean this because you talk on most of the published work, so I hope you also can share this PowerPoint to the community, if okay.
Yeah, the PDF or?
Yeah, no, PPT is better, because they're all published. That's and they will give, you can add enough reference. They know this is from Courtney.
Yeah.
Okay, that will be very helpful. Thank you very much.
Thank you, Paul, for running this series.